Alright, now we come to the effect of organic solvent. So it really depends on what type of solvent and how much is added, right, in terms of its effect on the viscosity. For instance, if you add methanol and water, the viscosity increase up to 50%, right? The reason is because you have a very good strong hydrogen bonding between the methanol with our OH group, interacts with the OH group of the water, so it's very tight here, and therefore it will increase the viscosity and then decrease. But if you add acetonitrile to water here, it will decrease, right, the viscosity from 0 by 100% to acetone. So you see that the effect of adding water to two different organic solvent has a different effect, right? So in C, most of the time we prefer to use acetonitrile based on experimental findings. What the conclusion here is that the effect of different kinds of organic solvent, even though you have certain form of hydrogen bonding or not, on the EOF may be proportional to the epsilon over your nu. So we can seek to control the EOF by chemical modification of the capillary of the inner surface here. So we don't assume that, right, you purchase a capillary, there's always internal filled silica, that's it. We can do some coating, right? We can do some coating of polymer of some sort. Now, because chemicals can be bonded to the surface of the wall, right? Let's say you have some ions, it's just tightly bound, right? Then there's no way that you can remove it because the bond is so strong. How? Are you going to separate it? No. So you want to coat it such that your analyte can move, right, and be separated due to different speed. So what we do is, right, we can do a dynamic coating, right? We inject through a narrow bore here some kind of polymer, right, that still remain to have some this cavity so that you can pass through analyte here. We can apply this chemical modification so that we have a lower amount of EOF due to the shielding of charge from the capillary wall. Remember, when your O minus of the silica is exerting too much influence of the charges here, then there's no shielding. And of course, the viscosity does also causes some effect that we talked about in the last slide. And we have more drag force here. We don't want drag because drag causes band broadening. So some of the polymer that at least I've used before is your polyacrylamide and a polyvinyl alcohol, right, to modify the capillary inside here. And you see that by doing this modification, we can also allow the inner wall of the capillary to have some of these non-polar property, right? So for dynamic coating, surfactants and hydrophilic polymers have been used. So the CTAP is one of them, which is a cation surfactant, acetyl trimethyl ammonium bromide. So here's the part about how do we measure EOF here. Very important when you do research using CE, have to know, even do experiments. So the first one is inject a uncharged neutral marker, which is detected, right? So nm is not nanometer here, it's a neutral marker. Now the VEOF is the LE over the T and nm. So why neutral marker, right? Why not charged? Because, right, when we change the voltage, it is not affected. Remember, if it's charged, then when you apply higher voltage, it will be yielded faster. Migration time will change. But neutral marker, no matter how high or how low the voltage, it's always there because it's neutral, right? Just the mass effect. So we can see that, oh, if we increase the voltage, yes, the other signal become closer and faster to the marker, but then the marker doesn't move. So this LE is the effective length of the capillary, the distance from the inlet to the detector. So later on, I will bring you to the class, right? We will bring a detector and show you what is the length of the capillary, what is the length of the capillary, from the detector, the inlet. So what's the difference there? I will burn a window for you. And the TNM is the migration time of the neutral marker from the inlet to the detector. So what are some criteria to choose a neutral marker? Of course, it must be neutral. How to be neutral? It cannot be charged, right, if a buffer pH is used. So because buffers, right, has a pH dependency, if you have some varying pH, right, and if that marker has some kind of ability to bond H plus N become charged, then it's moving. You cannot do it. Next is it must be detectable. Because after all your substances and your marker must be detected by the window, either the UV or the fluorescent and some other detections. If it's not detectable, there's no signal, then there's no reference point. Next, it must be pure. There's no interaction with the capillary wall. We don't want to be stuck inside such that, right, oh, maybe after 10 minutes, oh, then I see another peak. What is that? It's a neutral marker. It shouldn't be. It should have come up already. So there should be no interaction with the capillary rod. Just come out first because it's neutral, it's masked. And then of course we should have a soluble in the buffer, because if it's not very soluble, it becomes like a solid, it's stuck. It will affect the movement of the other substances of your sample. So some of these neutral marker we use methanol, acetyl oxide, formaldehyde, depends on the solvent the buffer use. Now the second method is the gravimetric method. Gravimetry, you know, is about mass, right? So we will first weigh the buffer, right, that's being flushed out of the capillary for a given period of time, and then we measure what is the amount of this buffer here. But this is not very good because, right, buffer, as you know, is a solution, it's a liquid. So there might be some evaporation that we are not aware of, you know, the temperature change due to the joules heating. It might be not so accurate. But can we do? Can do if you want to. But just that compared to the first case is not so reproducible, accurate. Okay. Now, there's something called the reversing EOF, and what is that here? When we analyze only anions, so suppose you have a pool of fluoride, chloride, sulfate, carbonate, right, in the sample, just anion separation. It is desirable to change the direction of the EOF, right? At the same time, change the polarity of the applied voltage. So, which means instead of a positive 30 kilovolt, we change to negative 30 kilovolt. So the modules are the same. But why change it? Because of the direction, right? And it will cause the anions to migrate faster so that we can reduce the separation time. What it means is, right, if you do not change the direction of EOF for anions, right, then it will come at the end. So you're wasting the front part here. No signal because anions doesn't come out first. So what for? You waste time and energy. But if you change it, you know that they're going to cluster and come out because of the charge. So why not you change the EOF and then they get eluted out first, and after that you don't need, you just can stop the process. So how do we do this reversal of the EOF? Now some additions, we have quaternary amines, we have the CTAB, CTAC, these are your N plus, right? TTAB, TTAC, tetracetyl triamino, ammonium bromide chloride, and then proteins, your alpha lactalbumin here. Your test exams are open book, so don't worry about memorizing it. Now, so in a schematic diagram, remember the top bar is the wall, right? You have your filled spare silica surface, right? And you can see that now pH must be pretty high so that the oxygen is oxide, right? So then it will be attracted to the quaternary amine, the first layer, but because it's amine, there's a lot of methyl groups here that's hydrophobic. So what it does is it does an interaction, right? And then it forms this kind of tails in the middle of this layer here. So what it means is, right, this layer become a bit thick, right? But at the other end, you see that because you have a discharge interaction, so you produce a negative ion, counter ion for this attraction, which means that now the electroosmotic flow is the other side. Compared to the just now, if you look at some slides ago, we do not have this quaternary amine. It doesn't reverse the polarity. It's minus, plus, minus, and plus. Remember, it's opposite. But here, because of this tail, they interact, right? The hydrophobic interaction. Then it become plus and then minus. So the anions, right, which is solvated inside the water medium here, then you just migrate towards the anode, right, and this direction you've shown. Okay. So in another diagram, I want to illustrate the importance of controlling EOF in terms of direction. So this is the anode, right? Cathode, attractant ion. So normal flow is this way. No flow because no charge is this way. They just hang in the middle, right? But if there's reverse EOF, you see this quaternary amine here. Then you just go the opposite. So you look at here, plus, nothing, neutral, plus, minus goes the other side, opposite. Now the order of migration of ions, right? So now that, okay, we reverse the EOF, but let's talk about normal EOF, neutral. Okay, cations and anions here. Now, when we move the EOF from left to right here, what goes to the cathode fastest? Of course, the opposite charge, right? Opposite charge, and then the higher the charge, the faster it moves, due to the electrophoretic property. And then what if same charge? Of course, the smaller it is, the less bulky, the faster it moves, right? So the bigger, heavier will be slower. Neutral in the middle, because there's no repulsive forces or attractions, it's just neutral. Negative because of attraction holding back from the anode and the repulsive forces from the cathode, it'll be slower. So if you have a double negative compared to a single negative, it'll be much slower. If you have this way, right, it's also slower. Okay, so it's the opposite. Okay, because you have to see it's not just one direction. You have to see that, hey, this anode is also holding back the anion. So that's why this is closer to the anode compared to the bigger one. If you do a reversal of the EOF here, it's just the opposite, right? Do you see? Yeah, so just be careful of the sign, the cathode anode directions, and the speed. Okay. So another diagram to just show in case you prefer some lines here, right? I think it's just mentioned the same thing. So to detect the order of migration, like what comes up first, what comes up last, depends also whether you have a normal reversal of the electroosmotic force, which ions are going to come up first, right? Size of the particle, charges of it. Okay. Right. So here, electroosmotic flow from cathode to anode detector is here. So you can tell that, right, even if you cover anions, higher charge first comes out. Okay, comes out first means on the electrophoregram it comes out first. You have the shorter migration time. Okay, neutral particles in the middle, and what comes out last, which has a very high migration time, must be your very heavy, the doubly triply charged cations. Okay, next talk about next part of CE, the hysteresis of EOF, something about electroosmotic mobility and electrophoretic mobility, and lastly the parameters of separations, your peak variance, selectivity, and your resolution.